In this video, we'll be looking at vector field histograms. So the concept of vector field histograms came about in 1991 with Borenstein-Koren's paper. Before then, there are a number of other techniques available, like the virtual force field technique that we looked at previously. Their approach was really taking into account some of the kinematics of the robot, how it will actually move and navigate around, and how it can do this at a local level. So without having the full picture of everything that's around, using just the data the robot's able to see at any point in time. So the original papers from 1991, they came up with an enhancement called Vector Field Histogram Plus in 1998 and Vector Field Histogram Star in 2000. And so there's been improvements related to the usability and accuracy of these techniques over time. But really, what it's talking about is performing real-time motion planning. So detecting unknown objects, avoiding collisions with those unknown objects, steering towards a target, whatever that target happens to be, and considering all these particular things are happening at runtime and on the robot, we're talking about here what we call a local planner rather than the global planner like A-Star, where we've got a full map of the environment. We control those solutions beforehand. One aspect that we need to keep in mind that our sensor data is a bit suspect. It won't always give us exactly the same result. It'll change depending on what we're measuring, what sensors we're using, what angle those sensors are striking things at. There's a whole lot of things. Temperature and things like that can also play in there as well. And in 1991, these sort of techniques were primarily developed with ultrasonic sensors, which have significantly more noise associated with them and uncertainty compared to the more modern LiDAR sort of sensors. Having said that, these techniques are perfectly applicable to LiDAR sensors as well. And so the basic premise behind vector field histograms is we create a statistical grid that we encode all our obstacles in. So it's like a statistical grid that we looked at previously with the occupancy grid, where we've got a probability that a particular square in that grid is occupied by an object or something impassable. In our vector field histograms, we're really trying to model our robot dynamics and our shape as well, which allow us to steer towards a particular target, and we move our platform towards that particular target, rather than just assuming that the robot is a point source in its histogram grid that it's within. So if we look at MATLAB, for example, there's a number of dimensions associated with that and looking at the shape and size of the robot. So we've got things associated with the robot radius, safety distance, if we want a larger distance around that robot to avoid obstacles. We've got our minimum turning radius there, so how quickly can the robot turn, and we've got distance limits associated with how well we can measure things based on the sort of sensors that we're actually using. So how does it actually work? Well, firstly, we have a world model, and that world model we have a 2D histogram grid, something similar to our occupancy maps that we had previously. It's a bit simpler in how it's encoded, but essentially each of these cell values encode a probability that there's an obstacle in that particular cell. What we then transform this grid into is a 1D polar histogram. Basically, we center this around the current robot location, so where it is at a point in time, and instead of having a square grid, now we've got a polar coordinate with the robot at the center, and we're measuring how far each of the obstacles or the probability of having an obstacle is at each of those points. And we can deconstruct this and map it out as a traditional histogram where we can see a whole lot of peaks and troughs there. Essentially, the peaks there are areas where there's a much higher probability of an obstacle being there. Each of our sectors there, or each of our lines, we assign a polar obstacle density, a pod variable. Those peaks, with higher ones, we can have a high degree of confidence there's an obstacle there, and the valleys tend to be a whole lot clearer. We set a threshold at some point there, which will be a threshold, basically a distance apart from the robot. And basically valleys below these thresholds are what we call candidate valleys, where we could move through, and it looks like it would be clear. We could probably move our robot through that particular candidate valley. Now what we do is we typically first pick the candidate valley closest to the target that the robot can actually fit through. There's no point picking a candidate valley that's too small and the robot will get stuck, so we're thinking about the robot kinematics and the size of the robot and things in there and how it can actually move into that particular area. We see in the bottom diagram there the histogram mapped onto what's actually happening around it, and the actual threshold value there that's actually quite close to the robot, and the valleys there, those 3 particular valleys, and we pick the one that's closest to the target and say that's where we're actually going to head towards, because that's a clear way that we can move towards. Well, now I'll show a brief simulation that shows how this might happen in practice.